Dear all, this is the fourth chapter of ME 306. We will do a brief introduction to compressible flows. Up to this point, we mostly considered incompressible flows and said that compressibility effects are negligible if the Mach number, which is the characteristic flow speed divided by the speed of sound, is less than 0.3. For these cases, density changes are negligibly small. Although the majority of engineering flows behave as incompressible, there are compressible flow applications also. Examples are the flows inside gas turbines or spacecraft nozzles, the flows over high-speed trains, missiles, or aircrafts. In this chapter, we will mainly study one-dimensional internal compressible flows, such as those seen in nozzles and diffusers. So let's get started. In this chapter, we will only study ideal gas behavior, and we'll start with a short review of ideal gas thermodynamics. Here is the ideal gas equation of state, relating pressure, density, and temperature. R is the gas constant, and T is the absolute temperature measured in Kelvin. For an ideal gas, internal energy, shown here with the letter U with an overbar, is a function of temperature only, and how it changes with temperature is defined as the specific heat at constant volume, CV. CV in general varies with temperature, but for moderate temperature changes, it can be taken as constant, which is what we will do in this chapter. Considering CV to be constant, we can integrate this equation to relate the change in internal energy between two states to the change in temperature of those states. Enthalpy is a frequently used thermodynamic parameter. Its definition involves internal energy, pressure, and density. For an ideal gas, it can be expressed as internal energy plus RT. The rate of change of enthalpy with temperature is defined as the specific heat at constant pressure, Cp. Similar to Cv, Cp will also be considered as constant in this course. The difference between the two specific heats, Cp minus Cv, is nothing but a gas constant R. Air will be the most commonly used gas in this chapter. Its Cp, Cv, and R values are shown in this slide. These are actually the values at 300 Kelvin. And this table shows how they change with temperature under the ideal gas assumption. As you see, Cp of air increases with temperature. Its change between 300 and 1000 Kelvin is about 13%. Cv also increases with temperature. Between 300 and 1000 Kelvin, it changes about 17%. Specific heat ratio, Cp over Cv, decreases with temperature. In the same temperature range, it changes about 5%. Specific heat ratio, shown with K, is very commonly used in compressible flow calculations. In this course, we will take the ratio as 1.4 for air. Entropy is another commonly used thermodynamic property. Here you see the famous TdS relations, one written for internal energy and the other for enthalpy. Integrating these relations between two thermodynamic states, 1 and 2, we get relations for the change in entropy in terms of changes in temperature, density, and pressure. In this chapter, we will not make use of the second law of thermodynamics that much, and our use of entropy will mostly be limited to the definition of isentropic process. We will be studying isentropic flows, which are idealized flows with no heat transfer and no friction, meaning inviscid flows. For isentropic flow, entropy remains constant. If we set the left-hand side of one of the integrated TdS relations to 0 to fix the entropy, we can derive the famous isentropic relations between the temperature ratio, density ratio, and pressure ratio of states 1 and 2. As an exercise, Try to derive these relations and have a look at your textbook if you need help. The easiest way to remember these relations is this equation: P over rho to the power K is constant, which is valid for an isentropic process of an ideal gas. Knowing this equation, the remaining details can easily be derived. Mach number and the speed of sound are two very important parameters for compressible flows. After calculating the Mach number, using the characteristic flow speed and the speed of sound, we can classify flows to be incompressible, subsonic, transonic, supersonic, or hypersonic. Mach number equal to 1 is known as sonic speed. This corresponds to the flow speed being the same as the speed of sound. In subsonic flows, Mach number stays below 1. Density changes are important, but shock waves, which are finite amount of property changes in infinitesimal distances, cannot occur. This is the Shanghai magnetic levitation train, the fastest on Earth. It can travel at 430 km per hour, corresponding to 0.35 Mach number, barely exceeding the incompressible limit of 0.3. Tomahawk is a subsonic cruise missile. It flies at a speed of 885 km per hour, corresponding to a Mach number of 0.74. Transonic flows occur around Mach number 1. Shock waves can be seen, and there can be both subsonic and supersonic regions in the flow field. A typical airliner cruises at 10 km altitude at a speed of about 900 km per hour. Using the speed of sound at 10 km, Mach number becomes 0.85. Air accelerates as it passes over the wing, and speeds exceeding the sonic speed may occur. In a supersonic flow, Mach number is higher than 1 everywhere in the flow field. Concorde was one of the only two passenger aircrafts that can cruise at supersonic speeds. It could reach speeds exceeding twice the speed of sound. It is no longer in operation. Hypersonic flows are those where the Mach number exceeds 5. Boeing X-51 is an unmanned research aircraft. It completed its first powered hypersonic flight in 2010. Space vehicles also experience hypersonic speeds as they enter Earth's atmosphere. Let's continue by defining sound and speed of sound. Sound is a vibration that propagates as an acoustic wave through a transmission medium such as a gas, liquid, or solid. Acoustic waves are a type of energy propagation through a medium by means of adiabatic compression and decompression. Here you see an animation of a series of such compressions and decompressions that propagate the wave. Note that although particles attain a certain speed as the wave passes over them, there is no bulk particle motion. Sound propagates through fluids as longitudinal waves, such as the one shown here. What propagates as sound is actually the infinitesimal deviations from the equilibrium pressure. Speed of sound is a fundamental material property, and it is defined as the speed an infinitesimal pressure wave travels in a still medium. For air, at standard conditions, it is equal to 343 meters per second. The exercise in this slide demonstrates that speed of sound depends on the medium and also the conditions such as the temperature of that medium. You can find the asked speeds in proper references. Let's derive an equation that relates the speed of sound to other fluid properties such as density and pressure. For this, consider a long duct filled with stationary gas. There is a piston at one end of the duct, and we push it slightly to generate an infinitesimal pressure wave. This wave will move at the speed of sound, and an instant of its propagation is shown at the bottom figure. As the pressure wave passes over the fluid particles, it creates infinitesimal changes in their properties, such as pressure, density, temperature, and speed. Ahead of the pulse, the gas is stationary with initial properties. We will consider a control volume around the wave moving with the speed of sound and write conservation equations for it. For an observer fixed on the ground, the propagation of the sound wave is an unsteady process. To make the derivation easier, let's consider an observer moving with the wave. For this observer, the problem will be steady. This change of reference frame will make the wave stationary and will alter the fluid speeds on both sides of it. Now the fluid ahead of the wave is seen as moving towards the wave with the speed of sound, and the fluid behind the wave is seen as moving away with the speed c-dv. Fluid properties such as pressure, density, or temperature will not be affected by this reference frame change. As seen, those behind the wave are different than the ones ahead of the wave by infinitesimal amounts. Now consider a control volume around the wave. This control volume has one inlet and one exit. To derive an equation for the speed of sound, we can make use of the mass and momentum conservation equations written for this control volume. This is what the first exercise in the next slide is about. The first exercise in this slide is about deriving the speed of sound equation. Please try to derive it by combining the mass and momentum conservation equations. If you need help, you can find a detailed derivation in your textbook. According to the resulting equation shown here, sound speed is the square root of the derivative of pressure with respect to density. The subscript s seen in the equation indicates that sound propagation is an isentropic process. As a historical note, Sir Isaac Newton worked on deriving this equation and made a famous error. He assumed the process to be isothermal instead of isentropic and derived an equation that predicts the speed of sound in air 20% lower than what it should be. But note that this was 180 years before the proper basis was laid for the second law of thermodynamics. The second exercise of this slide is about the possibility of using the energy conservation principle to derive the speed of sound equation. You can also find the details of this one in your book. The third exercise asks about the sound speed in a perfectly incompressible fluid, and the answer is infinity. Actually, it is possible to write the speed of sound in terms of the bulk modulus of elasticity of the medium, as shown here. Here we can clearly see how the speed of sound is a material property. Speed of sound is larger in fluids that are more difficult to compress, which are the fluids with higher bulk modulus. A perfectly incompressible fluid will have a bulk modulus of infinity, and hence speed of sound will be infinite. The final exercise of this slide is about deriving a more practical speed of sound equation for an ideal gas. This can be done by using the ideal gas equation and the isentropic relations that we discussed earlier. The resulting equation says that speed of sound of an ideal gas is the square root of specific heat ratio times the gas constant times the temperature in Kelvin. Try to derive this equation and get help from your textbook if you need. Let's study the propagation of a sound wave a bit more and try to understand why the speed of sound and the Mach number are such fundamental parameters of compressible flows. In this slide and the next 3 slides, we will consider the sound emanating from a point source. In case 1, considered here, the sound source is stationary and generates the sound waves shown. You can think of it as making a beep sound at a constant frequency, such as every 1 second. The waves are symmetrical in every direction with respect to the source. Observers located at points A and B will hear the same sound pattern. In the second case, the sound source is moving towards right with a subsonic speed, that is with a Mach number less than 1. It still beeps at a constant frequency, but the observers located at points A and B will not hear the same sound pattern. The waves get squeezed towards right, and the observer at point B will hear a higher frequency sound than the observer at point A. This asymmetry in the sound pattern is known as the Doppler effect. We experience this, for example, when an ambulance with its siren on passes by us. We hear a higher frequency sound as it approaches towards us compared to what we hear as it passes by us and moves away. In the third case, we consider a sound source moving with the speed of sound, that is at Mach number 1. Now things start to get a bit strange. The source beeps at a certain constant frequency and it moves with the speed of the sound it generates. The waves again get squeezed towards right, but this time they all accumulate on top of each other, forming what is called a Mach wave, shown as the red vertical line here. It is the tangent line to all the accumulated waves. The Mach wave divides the domain into two, the zone of action and the zone of silence. If you are an observer in the zone of silence, you haven't yet heard any sound. Sound waves is how communication is transferred in a fluid. A fluid particle located in the zone of silence would have no way to know that an object is approaching at the speed of sound until the object passes by it. Therefore, it cannot, for example, get out of its way. This is similar to a fast-moving car approaching you. Imagine that you cannot see the car, but hearing is the only way to sense it, just like a fluid particle. If the car approaches you with a subsonic speed, you can hear it before it arrives at your position, and you can get out of its way. But if the car moves with the speed of sound, you cannot know that it is coming until it hits you. This is exactly what happens to a fluid particle that is in the way of an object, such as an aircraft moving at the speed of sound. The last bullet of this slide is about the Bell X-1 airplane. If you visit the suggested Wikipedia page, you can read the details of this experimental aircraft. The X-1, piloted by Chuck Yeager, was the first crewed airplane to exceed the speed of sound in level flight. In 1948, this rocket engine-powered airplane achieved speeds exceeding 1,600 km per hour. The final case is the source moving at a supersonic speed, that is more than Mach number 1. Now the source is moving faster than its own sound. This time the accumulated waves will form a Mach cone in three-dimensional space, shown here with the red lines. This cone separates the domain into the zone of action and the zone of silence. At any given instant, the source will be located at the apex of the Mach cone. When a supersonic airplane passes over you, you cannot hear its sound even when it is right above you. To be able to hear it, it has to pass by you and move far enough away from you such that you enter into its Mach cone. The angle mu, called the Mach angle, is the half angle of the Mach cone. It is inversely proportional to the speed of the source. It decreases as the source speed increases. The first exercise in the next slide asks for the derivation of an equation that relates the Mach angle mu and the Mach number for the supersonic case we just discussed. Here is a detailed drawing of the supersonic case. Consider that the sound source is located at point A at time 0. Moving with the speed v, it comes to point B at time 1 second, to point C at time 2 seconds, and to point D at time 3 seconds. The distance between these points is the speed v times 1 second, that is v. At the instant shown, the source is located at point D. The circles are the current locations of the sound waves generated at points A, B, and C 3 seconds, 2 seconds, and 1 second ago. The wave generated 3 seconds ago at point A is now tangent to the Mach cone. This sound wave moves with the speed of sound c, and in 3 seconds it moved a distance of 3c. Consider the triangle formed by points A, D, and the Mach cone line. In this figure, the Mach angle is shown with the letter alpha, and it can be seen that sine alpha is equal to 1 over the Mach number. This is the relation we are asked to derive. The second exercise of the slide makes use of this equation. A supersonic airplane passes over you at an altitude of 4 kilometers. The sound it generates at point A reaches the observer standing at point B 20 seconds later. The horizontal distance between the points A and B is 5 kilometers. Let's solve the first part of the problem, which asks for the Mach number of the airplane. Here we show in green color the sound wave passing from point B, which was generated 20 seconds earlier at point A. The blue line is the Mach cone, and it is tangent to the green arc. Mach angle mu is shown in 2 places, using the similarity of the triangles. As we derived in the previous exercise, sine of mu is equal to 1 over the Mach number. Sine of mu is also equal to the distance L divided by the distance AB. Using the given dimensions, sine of mu is calculated as 0.781. Taking the reciprocal of this value gives the Mach number as 1.28. Therefore, this supersonic airplane moves with a speed that is 1.28 times the speed of sound. Please work on the remaining parts of this exercise by yourself. This is the end of the first part of the compressible flow chapter.